Hi everyone, I'm Noa Ligot and I'm doing my thesis under the supervision of Pierre Delmel at UC Louvain in Belgium. My research aims for the development of quantitative tools to understand the risk of volcanic ash falls on agricultural crops. And today I want to share with you our findings and thoughts about the farmers' perception of agricultural damage after the last eruptive period of Tungurahua volcano in Ecuador. Volcanic soils are generally very fertile. To illustrate this, it is reported that they cover 1% of the emerged land, but feed 10% of the world population. Unfortunately, crops grown around active volcanoes are sensitive to ashfall as they endure various injuries from ash, leading to low harvests. Most active volcanoes are located in developing countries where agriculture is the main source of income and where rural population is generally poor and therefore vulnerable. In the event of an eruption, economic losses due to crop failure increase population poverty and thus increase its vulnerability. This is called the negative spiral of poverty. In this context, it is important to develop tools that quantify volcanic risk to crops. These tools are needed in order to strengthen the capacities of government, organizations, communities, and individuals to effectively anticipate, respond to, and recover from the agricultural impacts of a volcanic eruption. Risk of impact on an exposed asset is understood as a function of the volcanic hazard and the asset vulnerability. Ashfall hazard is well predicted by current advection diffusion models of the volcanic plume. Post-event impact assessment studies are used to collect data on crop vulnerability to ash. The crop vulnerability is commonly described as a relationship between the ash deposit thickness and a loss of productivity or yield. For example, an ash deposit of 1 mm is believed to cause very little loss to crops, while a deposit of 50 mm would lead to major losses. Current models of crop vulnerability divide crops into categories to assess their vulnerability. The classification is based on the edible part of the crop. We do believe that additional parameters come into play when looking at crop vulnerability. For example, the root vegetables category includes potato and onion. We expect that ash does not affect both crops equally because their morphologies are different. 1 mm of ash will probably affect potato, which has hairy and horizontal leaves, while it will not affect onion, which has smooth and vertical leaves. Another problem with current crop vulnerability quantification methods is that they are based on very little data because few studies exist. According to field observation, other ash properties, such as particle size and surface composition, may also modulate the level of ash effects on crops, while current methods only consider the deposit thickness. One last drawback of the current quantification method is that size-specific biophysical factors, such as climate and pre-existing vulnerability of the agricultural system exposed, are overlooked, while they are strong determinants of the eruption impacts. The objective of our study is to get new insights into the factors governing crop vulnerability to ash. We studied the impact of the 1999 to 2014 eruption of Tungurahua volcano. We received help from the Geophysical Institute of the Polytechnic School of Quito, which works with local farmers that have gained significant knowledge about the various effects of ash on crops. We interviewed farmers in 15 villages located in the high-risk area of ashfall. We gathered data on the main crops cultivated and the crop-specific calendars, the ashfall characteristics and their effect on crops, as well as the coping strategies and adaptations that farmers deployed during and after an eruption. All farmers reported detrimental effects of ash falls on their crops. The most common effect of ash fall is the discoloration of leaves from green to yellow. It's a condition called chlorosis that is due to leaf shedding by ash and that decreases leaves photosynthesis. After contact with ash, fruits are no longer sellable as they are scratched, rotten, or the skin is encrusted with ash. In the 15 villages, 30 to 70% of the farmers reported an average crop yield loss of 50% between 1999 and 2014. A consequence of the crisis is the crop abandonment in all villages and the replacement by more ash-resistant plants, notably white onion. We observe that crop yield loss diminishes with downwind distance of the source. Within 10 kilometers of the volcano, yield losses of 50 to 100% were reported. Above that distance, losses decrease between 25 to 50%. These observations are explained by the fact that ash deposit thickness also decreases with distance to the volcano. This is consistent with previous studies and suggests that deposit thickness is a key metric for predicting a reduction in crop productivity. The farmers from Tungurahua systematically refer to the white fine ash type as being the most harmful to crop plants. In order to shed light on the characteristics of the so-called white fine ash, we prepared a chart with 6 photos of Tungurahua's ash specimens that differed by their content in ash smaller than 63 micrometers. Farmers selected a photo showing tephra containing 20% or more of fine particles. This observation points to particle size as another important ash property beside deposit thickness that modulates impacts on crops. According to the farmers, crops in the flowering stage are most vulnerable to ash deposition. A few millimeters of ash are sufficient to annihilate the harvest, except for white onion and potato, for which bulb and tuber formation, respectively, does not require pollination. Another interesting finding is that plant surface and morphological characteristics modulate ash retention on plants and subsequent ash impacts. For example, raw and pubescent blackberry fruit retains ash very well as large multi-lobed and horizontal squash leaves. On the contrary, ash is easily washed off of smooth and vertical onion leaves. Based on the interviews, we constructed crop calendars for all crops. Depicted on the slide is the one of corn for the 11 corn-growing villages. The sowing months vary between May and October, depending on the village altitude, likely because it dictates seasonal distribution of rainfall. The vulnerable months to ash correspond to the flowering period and vary between July and December. In the study area, altitude also dictates the crop zonation. Between 1,900 and 2,600 meters, we found corn, potato, and fruit trees. This is depicted in yellow on the map. Between 2,600 and 3,000 meters, corn and potato are the only crops. It corresponds to green on the map. Knowing both the spatial distribution of a given crop and its altitude-dependent cultivation cycle, we can outline how its vulnerability to ash varies throughout the year. Here is an example of the spatial and temporal vulnerability of corn. October and November are the months during which most ash damages to corn are expected around Tungurahua volcano. In this presentation, we saw that crop vulnerability to ash is poorly understood and that current approaches based on ash deposit thickness and grouping crops into categories tend to overlook important variables. Future approaches should consider additional factors such as ash grain size, crop growth stage, and crop morphology in order to gain a better understanding of ash impacts on crops. The crop-specific calendar is a simple and informative tool to assess crop vulnerability. So this brings me to the end of the presentation. Thanks for your interest, and I'm very happy to answer any question.